Namaskar, Jai Guru. As we have studied about electric charges, conductors, insulators, charging by induction, basic properties of electric charges, Coulomb's law, principle of superposition of charges, and many more things in the previous lectures of the chapter Electrostatics. In this lecture, we are going to talk about electric field lines, or you can say electric lines of force, and electric dipole. I am Ritesh Kumar Pathak, Department of Physics, Intermediate Wing of Yogoda Satsanga, Mahavidyalaya. See, according to the concept introduced by early scientists, whenever a charge of magnitude capital Q is placed in vacuum or space, it produces a force everywhere surrounding of its own, and that force is due to the field which is known as electric field. For that, we have assumed a positive charge of magnitude capital Q in vacuum at origin O, and at a distance r from it we have taken another positive charge which has the magnitude small q. Now, according to Coulomb's law, the charge capital Q will exert a force on a small q charge is given as F equals to 1 by 4 pi epsilon naught capital Q into small q upon r square, which is the distance between them, and we have assumed this as equation number 1. On the other side, the magnitude of electric field produced by the capital Q charge at a distance r from it will be capital E equals to 1 upon 4 pi epsilon naught capital Q upon r square, and it is supposed as equation number 2. From both the equations, we can calculate F equals to Q into E, and therefore capital E equals to F upon small q. Hence, we may define the electric field as the electric field due to a charge at a point in space may be defined as the force that another unit charge would experience if placed at that point where we have taken a capital Q charge earlier. Now, the electric field is a vector quantity and its SI unit from the formula as Newton per Coulomb, and we may write the dimension after calculation from this formula again, m l t to the power minus 3 a to the power minus 1. The electric field is a characteristic of the system of charges and is independent of the test charge that we place at a point to determine the field. So we have to introduce electric field lines or electric lines of force. This concept was invented by Faraday to develop an intuitive non-mathematical way of visualizing electric fields around charged configurations, and he named them as lines of force. Therefore, an electric field line is a curve drawn in such a way that the tangent to it at each point is in the direction of net electric field at that point, and these lines will be around the charges. Here in the first picture we have taken a positive charge, and we can see there are some lines which has the direction radially outward and which is showing the field is in outward direction, since electric field is a vector quantity, and therefore we can say that electric field is a vector field. On the other hand, there is a negative charge where we can see these field lines are radially inward. But in the case of two charges which have different polarities, they are positive as well as negative, therefore then the electric field lines appears to be starting from positive charges and ending up to the negative charges, but they never intersect each other. Later on we will see the property, but before that, if we will have two charges having same polarity, or we can say they are like charges, these field lines appears as they are repelling each other. So that we have seen in the diagram 4. Also we have some general properties of electric field lines. The first one is electric field line start from positive charges and end at negative charges. If there is a single charge, they may start or end at infinity. Secondly, they are discontinuous curves. Means they do not form any closed loop. Third thing, two field lines never cross each other. Number 4, as we have discussed, electric field lines do not form any closed loops. And the fifth one, which we have already learned, that tangent to the line of force at any point gives the direction of electric field at that point. These are some general properties of field lines. Further, we move to the topic electric dipole. Whenever we take a pair of equal but opposite point charges separated by a distance 2L as per convention, then we found an electric dipole. Here you can see the diagram. We have taken two charges as plus q and minus q, and the distance between them is 2L. Here we have also considered a center, which is the midpoint of location of charges, and which is known as center of dipole. The total charge of the electric dipole is obviously be 0, as they have different polarity. These two charges are negative as well as positive, but that doesn't mean that the field is 0. There will be some field, and that electric field of the pair of charges at any point in space may be found from Coulomb's law and by the use of superposition principle. Here for the dipole we have to discuss another topic, which is electric dipole moment, which is defined as the product of magnitude of either charges and the distance between them is called electric dipole moment. Mathematically it can be represented as vector P equals to Q into 2L. Now since this is a vector quantity, that means there will be some definite direction. So the direction of electric dipole moment is from negative charge towards positive charge within the dipole, and we can assume the magnitude of the electric dipole moment as P equals to 2QL. There are some physical significance of dipoles also, and they are also related to electric dipole moment. In most molecules, the center of positive charges and the negative charges lie at the same place, and therefore their dipole moment is 0. However, they develop a dipole moment when an electric field is applied, and those molecules are like carbon dioxide, methane, etc. On some other molecules, the center of negative charges and the positive charges do not coincide. That means they have a permanent electric dipole moment even in the absence of an electric field. Such molecules are called polar molecules, and we can take water as its one of the example. I have tried to give the idea about the electric dipole, electric field and electric dipole moment, but if still you are facing some problem, please leave your doubt in the comment box. Thank you. Jai Guru.